In this video we'll look at some of the different aspects of profiling, which is the measurement of displays to get an understanding of their capabilities and characteristics, and is used as the kind of precursor to calibration, especially if you're using 3D LUTs for the calibration. If you're doing manual calibration, then it can become part and parcel of the same process. So if we open up ColourSpace, and the initial component is obviously the profiling menu, which if we open up, and just to set up a bit of an environment for ourselves, we'll do a control click on a few of the options that we have so that we can set up a bit of a layout to give us the basic understandings as to what we've got, including a patch window so that you can see what's going on. We'll just for now we'll move the main ColourSpace window out of the way so we can see the graphs. You can see that we've just got a zoom in to the CIE graph for the different primaries, the standard EOTF gamma graph, a differential version of the same graph, and RGB balance. We're just going to use those while we're taking some measurements to get a feel for what's going on. Okay, but the first step in any display calibration is to first make sure that the display is in its uncalibrated state. That depending on the display, you may want to actually connect to it and upload a null LUT. So we're using a Chroma broadcast monitor here, so we can actually connect to that using this IP address. And then with Unity bypass selected, because there are no other LUTs in the system, we can just upload, and that will load that into the system so that we know that the display is in an uncalibrated state. Now we're not going to actually use the internal patch generator, so for now I can disconnect the display again. And when we go back into the manual measure menu, we're going to actually use the test patterns to manually set up the black and white point of the display such that there's no clipping or crushing. So if we select brightness, enable, and you can see it flashing there with the test pattern, and if we double click it, we get it full screen, and we can now bring up the display's own menu and adjust the controls until we get it to the point where we think it's just about right. Again, this is by eye, so things aren't going to be absolutely perfect at this stage. We'll go back and do the same with contrast, and what we're looking for is to make sure that the brightest patch just before 100% is almost just nearly visible, and that was the opposite to what we were doing with brightness, where we are looking for the darkest patch to be almost just barely visible. Okay, when they are done, we can actually then run a profile to see if what we've got is correct, as well as see if the black and white points are actually at the level that we want. Obviously we have little control over the black, that tends to be just the darkest that the display is capable of doing, but white we can obviously adjust to bring down the white or bring up the white, but without any clipping occurring. So if we run a quick profile, so let's just do a grey only large. We don't need drift compensation for this because there's not really enough patches to worry about. And we are just going to connect to our probe, which in this case is a colorimetry CR100 on port 9. We're not going to worry about probe matching at this stage because we can come back and do that later because it's retrospective. If you don't understand what that means, look at the video on probe matching, but we will come back to it here as well. So again, we can now just run a grey only quick profile, and you can see that it builds up in the CIE graphs as it's going. So here you can see the grayscale points being plotted in, including the tangent lines, which we can control in the graph options, so we can see what's occurring. Now at the moment we're looking at Rec 709 as our target colour space, but this display is obviously uncalibrated, so not only will the grayscale not be where it should be, but you can see that as well the RGB primary points are obviously considerably different to our target of Rec 709. Now more on that in a second, but for now we can see that we have an RGB balance where blue is considerably higher, and if we look at the grayscale here, you can see that the points are indeed heading towards blue. We can also see that the gamma is a little higher than target, and in fact if we look here, we zoom down the differential a bit, you can see that we've actually got two things, that the gamma is brighter, which means a lower gamma value initially. It then settles down and then it drops out a bit at the end where the gamma value becomes higher, which means the display is a little bit too dark at the end. Now you may see, if we just line that back up for us, there we go, if we look into the clip graph, so actually no, it's the while the gamma is out, we're not actually seeing clipping in the highlight, but we are seeing the same kind of effect where the display is brighter than target. Now it may be that we can set that a little differently. So what we'll actually do is we will look at the EOTF, and you'll see it in both graphs here. In fact, I'm going to go into the grayscale on the CIE, because what I want to do is look at the measured points. So if we click on black, you can see our target obviously is 0, but our display is actually higher. So what we're going to do is first of all transfer over the measured values into our target, so we can actually see whether or not the measured points relative to the black and white of the display actually align. If we use the sliders to go up to white, which just selects the white point 255, we can see as well that it's 101.8 nits, so it's relatively close to the ideal of 100. Anyway, we're going to just go to the second point in the graph, which will at the same time pop up a little window with some information on the point we've selected. We can actually choose to see all the ones displayed, so we can see that out of the grayscale 8 is the lowest after 0, and then we have 16 and so on. So what we're going to do is, having picked the point, look at the information. We can see the target based on the black and white point of this display should be 0.1062 nits, but actually it's 0.1646 nits. And that's again what we're seeing here, that the measured value is higher than it should be, giving us this gamma offset. In fact, if we zoom into the gamma graph, not the differential, the actual EOTF graph, you can see here that relative to our black point, the first measured value is indeed higher, as is the second, as is the third. So it means that we do have a bit of an offset happening at the beginning, which actually is causing this lift in the graph. So what we're going to do is actually go back and say, well, maybe when we configured the brightness using our brightness test pattern, that we actually had it slightly too bright still. So what we will do is now simply measure, there we go, turn off, measure, say the second, third, let's have a look. We've got 0.2, 0.3, 0.4, 0.4. So I reckon we'll go with 0.3. So that will be 0816, that one there. Okay, and having clicked it, double clicked it, it's now set it up here so we can see target 0.43, actual 0.58. So what we're going to do is just put that into repeat and hit measure, and then I'm going to use the displays menu, which you can't see, to actually select the brightness, and I'm going to bring that down a bit. So you can see that as I adjust it, the measured value is coming down, and you can see that on our differential graph here, and if I zoomed into it you'd see it on the gamma graph as well. So I'm not going to bring it quite all the way down, but just enough to get us a little closer. So I want to see what effect this has. So actually we'll go down to about there. So we're not quite as low as the target, but we're significantly lower. Now the reason for that is that having made that adjustment, I now want to rerun our grayscale to see what effect that has had on the overall response. Now the existing graph will stay here until it finishes. These graphs presently don't update when you're doing a automated characterization. They will when you're doing manual point by point, but not during an automated characterization. So we'll let it run through. Doesn't take too long with the CR100 here. There we go. So now we can see the effect that that's had. It's significantly changed the initial slope, and if we look at the clip, yeah, we've still brought it down significantly, but we're starting to see a dip. What that means is we don't want to go much lower, because this looks like this is going to pull down the initial coming out of black, but if we push it too hard, it'll be very hard for it to actually pull back from that. In other words, we will get clipping occurring in shadows. So I think actually we've got the best compromise there, so we're going to stick with that. Okay, I'm going to back out of the menus, see, again, not that you can see them, and we've basically got our black and white points set, and we're now looking at a minimum of 0.812 and 98 now. So we brought that down, and we may want to bring that up slightly. It will drop slightly when we calibrate because the blue is high compared to the red and green, and to correct that we will end up reducing that value further. So we may want to bring it up above. In fact, let's do that. Let's just bring that up a little bit above the 98, so we're above 100 by a bit, to allow for this correction when we perform that. So again, I'm back into the menu of the display. We will go into our patch, select white, go into repeat measure, and now I'm going to start to make some adjustments to push that up. Bring that up slightly. There we go. You can see, and you can see the graph responding. So looking at the clip here, so obviously we're going brighter. So again, compared to the previously measured points, it will look like there's a clip occurring. There obviously isn't. Just these points have not yet been remeasured with the new value. And I think we'll take that up just a little bit more. There we go. I'm going to work with that one. And back out of the menu again. And go back in and do another quick profile of grey only large. Okay, and there we go. So that's going to be our initial starting point. We've moved it so that, yeah, we're 104.9 and 0.0864 in the black. So that's going to be our starting point for this display based on the limited user controls we have for the display itself. Okay, now before we get into running a full profile, one of the interesting things is that we're obviously looking at this display at the minute targeted to Rec 709, while it's actually in its wide gamut mode. Now it doesn't matter where we look in the different displays, but you can see the errors that we're going to obviously have visible because the display is in wide gamut uncorrected, but we're targeting Rec 709. So a neat thing to do before we start to take this further is to actually generate a new color space specific to this display, so that as we're measuring it, we're actually comparing it to itself. And that way we are going to end up with graphs that have a much better representation of what's going on and the underlying potential issues than if we just look at it relative to one of the fixed color space standards. So I'm going to bring the main window back in again, and we will go into the library. Let's just turn off the patch window for a second, and we're going to save the profile we've just done, and we will call it Chroma No Probe Matching. Okay, so it's now Chroma No Probe Matching, and it says it's a grayscale profile. And what we can do with that profile is use the modify function to extract a color space. So we will just add onto this extract, or EXTR, and say extract space. Now this will try and get an average for the gamut and gamma EOTF of the display. So it ain't going to be 100% because we've only got 3 color points with the grayscale, and it will be close, but it won't be absolutely perfect. But it will be perfect for what we need it for. So again, just get rid of that. We now go into settings and we select our target to be Chroma EXTR, and you can see straight away that we're now comparing the measurements to the actual capabilities of the display. So the RGB balance looks better. The gamma is going to be pretty much the same because the extracted space will be doing a power law, but it's just aligned it a little bit better around the center line because it's targeting the actual value rather than the fixed 2.4 of Rec 709. Anyway, what you can see in the graphs though is obviously we've lost our zoomed point because we were zoomed into Rec 709 in those areas like that, but obviously we're now looking at the wider gamut of the display. So we just need to recenter these so that we can see exactly what's going on when we're doing a bit more measurements in a minute. So we will just align each of the primaries again, and you can see that they're pretty close to the new target, but not 100%. And that's because we've only got the one value of primary colour in a quick profile that is grey only. If I had done a primary only, then we'd have more information for the primaries, and they would have been a little bit more accurate. But again, very close anyway. But it means we can now see what's going on a little better. So what we'll do now is run a much larger cube profile. So we'll do a 21 cube. We will use drift compensation. The colour we're going to use is a pretty standard 240 grey. So it's bright but not 100% white. It needs to be relatively bright. It's no good having a kind of a 128 patch because that will actually be brought down even more by the inherent gamma in the display. So you want something that's around about the 240 mark, which is the kind of the default in the system. And we're now going to be doing 9,447 patches, obviously variable time because it will take a different amount of time per patch based on the darkness or brightness of the patch and the probe in question. As I say, in this case, a CR100, and we will just kick that off. And when it's measuring, because we are targeting the native gamut of the display, we actually get information that is quite useful in the sense of feedback. So we can see that obviously the very dark patches have got a low saturation, they're desaturated, which is normal for an LCD display of this type. And you can see if we look at it in the volumetric mode, you can see that it's the lower patch colours, they really are right down at low, that are obviously showing a level of inaccuracy as expected, whereas the brighter colours are actually matching up quite nicely to their target, as shown by the green colour of the delta E dots, compared to, if we look at the colours down here, we can see that, here we go. You can see that we've got red and orange in the black or in the shadows, but again, relatively small errors in the great scheme of things. And we can just sit here and assess what's going on while we are looking at the profile happening. And we can obviously change into the other CIE graphs to see the results there as well. As I said before, the 1D graphs do not update. All of these ones do. So if we zoom out slightly here, we can see that where the points, and again it's because of these are the dark measured points, are showing us where they should be. And we'll let that run. As we can see, we're some 6,600 patches through, so 2/3 of the way through, and the graphs are slowly building up, showing us all of the relevant information based on the ColourSpace that we built from the original grey only quick profile. Just move that out of the way, and you can see that in all of the zoomed in graphs, so you get an idea as to what really is happening with the display while we are profiling it. The tangents also help show that there may have been 1 or 2 errors. We can actually see straight away here that there are 2 readings that really have very bad measurements on them. So something's actually gone wrong at that point, and that may just be as simple as me dragging the main window past the patch. But again, no problem, because we can go back in and actually use that data to remeasure just those patches a bit later. And if we go into graph options, for example, we can look at just the red errors, get a feel for what we've got going on. And there you go, we can see that we have 2 fairly large luminance errors, luminance because they are obviously vertical, and a slightly smaller one there, and we can get a feel for where they are in the graph, and we'll be able to pick those up in the 2D graphs. At the moment we can't select points in the 3D graph, but we can obviously go in and find them in this graph a little bit later on. There's no point doing it now until the profile is finished. If we go in and look at the cube-based graph as well, then you can get a feel for where the errors may be and quite how large just those 3 are specifically. Obviously the ones we're seeing here are around the black area, black point of the cube, so obviously these are our expected errors in the blacks and shadows. We'll just let that carry on and come back to it in a bit. And we're getting towards the last few patches now. And then we'll go back in and look at the data, and when necessary make some corrections. The reason for the errors has just become very apparent. When I start the recording software, it dims down the screen while it does its 3, 2, 1 countdown, which I'd completely forgotten about. So that's why we do have some errors in the patches. And looking at the final few as they build up. There we go. And there we go, characterization complete. Duration just over 2 hours, 10 minutes. So now we can actually assess exactly what is going on, where we can see the rather large errors that I've obviously created myself through stopping and starting the recording software. So if we start by looking at the red, there we go. And you can see we got a couple of fairly serious errors in there, but not that many. So what we're going to do is isolate those. So if we look over 5 for the delta E, and then we can select the particular particular point that we're interested in, and then we go back into our view, we can see that indeed that is one of the errors, because it has a delta E of over 5 and the cross on it, so we know that's one of them that needs to be redone. And while parked on that, we can actually go back into manual measure. The sliders have, or will go to that when we've actually disconnected them. Obviously it's selected the patch color, but the sliders are representing a grey fixed around the one value because they were locked. It doesn't matter because the patch is the right color, but we can just prove that by going back in, clicking again, and there we go. We end up with the the correct value, and we can simply say measure. That patch has now been corrected. We can go back in and pick on one of the others. Actually, these up here to start with, I think. Indeed, we can see that's one of them. Again, another green colour, and we will measure that one. Error's gone. Back into that one. Again, you can see it on the end of the tangent, showing us that is indeed the one we want. Measure. And that one. There we go, that is indeed that one. Measure. And then we can see obviously the ones down in the absolute shadows we know are not going to be an issue. That one there is. So that is pretty much on the edge of the magenta there. So we should be able to locate those actually too close together there. Interestingly, to help, you can see that we know the errors are luminance. Those 2 points there show a luminance error because there is no tangent line in the XY coordinate like these ones, which shows a saturation error. So it must be those ones. And indeed, there we go. There's the first one. Measure. That one there. And again, there you go. That's it. Measure. Point's gone. I mean, all the others are literally right down in the shadows and are gamut errors rather than luminance errors. So we've now got a profile that basically has the best possible. We could go in and check those if we wanted to, but because they are gamut errors in the shadows, there really is no point. We can now save the profile, and we will call this Chroma no PM, no probe matching. We'll just say it's a 21 cube 3. Oh. Cube 3. Okay, that is now in our library. There. Now, we mentioned earlier that we weren't using probe matching. Go to the probes. And if we look in here, we have not got a probe match for the chroma display. So we're now retrospectively going to do that. So we will go new. At the minute we've got the CR100 obviously. So this is chroma CR100. Okay. And measure all. That'll go through and measure the red, green, blue and white patches. And then we can disconnect that probe and connect the CR250, which is on COM9, and back into configure, and we will start a new profile, probe match profile, chroma CR250. The probe has been aligned onto the same point on monitor, and we will kick off and measure all. Again, it'll take a bit longer than the CR100 because it's a spectro, which is one of the major reasons why we match tristimulus to spectros. Okay, so we can now select the CR100 as the active and the 250 as the reference. And now, when we are in graph options, we can enable probe matching. You can see the difference that makes. Now obviously, activating probe matching is generating a greater level of error because we did not make the color space that we're using, the target color space, with the probe matching. It was the chroma no probe match extraction. So what we're going to do is, with probe matching active, resave the same profile. So we'll just save, and this time we're going to call this PM Active 21 cube 3. Okay, and when we go back into our library, that will now be there, and we can just turn off the patch for the moment. We can now extract from that using our modify another color space, but this time we will call it PM Active EXTR and extract that space, so that when we go into our target gamut, we have now got Chroma Probe Match Active extraction, and now we're matching to the tristimulus matched to the spectro. We can obviously update the luminance because the data there's dropped the previous values that we were using, and now you can see that when the probe matching is active, we're actually more accurate than without, because we are now using a new target color space based on the probe matching. And we can see that in blue, there we go, and red, as well as the gamut and the RGB balance. Basically, we now have our profiles ready to do whatever we want with them. So we have got one that we've saved without probe matching, one that we've saved with the probe matching burnt in, and we can use those to generate our calibration LUTs in the LUT generation side of the software, which will be in another video.